Okay, so in this section, we're going to introduce the idea of an inverse function. Right, so sometimes we introduce the junction of just a function as some input value going into this box, right? Some of this mysterious box that does some kind of operations onto it, and then the output is y, right? Which we sometimes call f of x. Now the idea of an inverse is, can we go in reverse, right? In other words, y, then there's another kind of mysterious box here that does something to the y, but what I want to know is, can I get back my input x? All right, can I get back exactly what I put in? All right, so this idea here of this box returning the input, right, from our output is this idea of an inverse, right? Usually this is what we would call the inverse. Right? And we want to see, all right, well, do all functions have an inverse? Right? An inverse of f. Right? Can I do this with any function? Right? So as it turns out that we can't do this for every single function. Right? But there are certain types of functions that do have an inverse, and there are other types of functions which, with the restriction of the domain, we can define this idea of an inverse. Okay, so we're going to define here what an inverse is. So an inverse function. So first of all, inverse function, f of x has an inverse if it is 1 to 1. Okay, so this idea of 1 to 1 is when we're talking about functions, right? We had this idea of a vertical line test. So this is a function, right? It passes the vertical line test, right? For each input, we have exactly one output. All right. All right. Now, in order for a function to have an input, in order for a function to have a inverse, it needs to be 1 to 1. So in other words, it has to be, right? So now we want to ask ourselves, is each output unique? All right. So in other words, right, for the output here, does it correspond to exactly one value of x? In this case, we could see, oh, it does not. Right? In other words, a way to determine whether a function is 1 to 1 is, does it pass the horizontal line test, right? Vertical line test tells me a function. Horizontal line test will tell me if it is 1 to 1. Right? So something like this, the output corresponds to two inputs. So it is a function, but this is not 1 to 1. Okay, so a 1 to 1 function will have type of behavior like this, right? Like our cubic, similar cubic type function, right? Or odd degree, a basic odd degree one. Not necessarily that all odd degree polynomials will have inverses, but this particular one, right? So it is a function that checks off that box, right? So it is a candidate for it having an inverse. It is in fact a function, so it must be that first. And it is also 1 to 1. Right? You see here. Each horizontal line corresponds to exactly one input. All right. So those conditions need to be met for having an inverse. Right. 1 to 1. Now, notation wise, right? We say if f of x is a function, we use this for our notation. And we read that f inverse of x. All right, keep in mind that this is not an exponent, right? So this does not equal 2. All right, so those -1 Superscripts here are not reserved for, are usually reserved to when dealing with function notation, right? So context is important when we're talking about a function. It's not an exponent, it's to signify the inverse of a function. Okay, so f of x is an inverse. So we need one-to-one and also properties of inverse if f of x is equal to y, that will be true if and only if f inverse of y is equal to x. Right? Now, in other words, what we have here is if we know the domain for f of x, switch my color up here. If the domain is D, some set, right? Written in interval notation, right? But here we'll just leave it very general, just some set D, and the range is some set R. The inverse of x, the domain now becomes the range, right? Because we changed the input and the output, and the range, oh, that's confusing here. The domain is the set R, and the range is the set D. All right, well, so that is kind of what this notation is telling. All right. Okay. Now, if given two functions and we're asked, well, are these two functions inverses of each other? Right? In order for them to be inverses, they have to satisfy this property, right? Another property of our inverses is that if we take the composition of inverse with f of x, the result should be simply the value of x. Even if we reverse it here, so if we do it this way, then both of these conditions must be true. Okay, so just make sure that you check, if given two functions, make sure you check both of these compositions, right? Because in general, it's not a rule that the composition is commutative, but if they are inverses, then it will be commutative, and that resulting operation will be simply the value of x. All right, so thank you.